ancient Indian mathematics. I mean, without getting into any controversy, this is a mere statement of fact these days that this ancient India, and particularly its science, has been hijacked by politics. So it is a very important thing to understand and appreciate that while we talk about this ancient Indian science, particularly in mathematics, there is already a trend of two contradicting doctrines. With due respect to everyone involved, as a searcher, as a student of ancient Indian mathematics, as a passionate follower of the whole episode, what I gather is this, that these two doctrines are completely, at the two different ends of a diameter of a circle. One doctrine is an age-old one, which is known as Eurocentric doctrine, Eurocentrism, which as an axiom accepts and believes that everything that modern day civilization has got is due to the Greeks' domination, the Greek invention. The Greece is the cradle of the modern science. It's a kind of axiomatic approach with this as axiom number one. And any rest of the argument should follow in consonance with this argument. That's a kind of doctrine, as Eurocentrism. And there has been recently another one, which is a kind of nationalistic way of looking at it, and where the claim again is that everything, each and everything, every iota or epsilon of knowledge was there in India, and nothing else is required. It was there. Everything is known to India, and there are so many claims, unfortunately, without much proof. Here proof doesn't mean proof of science. Proof of history is a different kind of ballgame altogether, but there is a way of justifying facts. But without bothering even a little, tall sounding claims are made every now and then. And as far as I understand it, by doing it, I think much, gain, it's not gain, rather, this is actually damaging the existing huge repository and information about this repository, in the sense that because the proofs are not being proposed or substantiated, the claims are, at the end of the day, it sounds like tall claims, some of them really hilarious. And the Eurocentric school, they are taking the advantage of this situation by tying up something, some very important thing that was really there with this, untenable claims, and putting them on the same bench. So these people who are doing this kind of tall claims due to their political perspective, to me, it appears that they are doing more harm than good to ancient Indian science. So what I'll be doing today is this. Whatever little bit of time that I have to discuss with you, this is such a lecture. If you look at the very first word that I have thought of, glimpses, it has to be in the tune of glimpses, because the whole edifice is a huge one. We cannot just get into all of them in 1 or 2 proposed hours. So we have to be choosy. We have to point out something. But even then, there are 2 different ways that one can think of for this kind of lecture. I can go on making, names of the great mathematicians of ancient India and just give you the name of their work, and that will make a very long list, and that will take the whole of my time. But I don't want to do that, because if I do that, then at the end of this lecture, you will also think that this is a kind of tall claim. So rather than doing this one, what I would like to do is this much. I'll just point out certain salient features and would like to dwell in depth, in details, every minute details with 1, 2, 3 such issues, so that you can make your own opinion. And what I believe is this: once you find it interesting, once you find it convincing enough, you will pursue it yourself. There is no dearth of material today. This Google and all such things, it's always there. So you can easily delve deep into the subject and try to gather more and more knowledge. So it's not really required that in a 2-hour lecture I have to tell about everything that I have, come to know in last 15 years with my passionate study of these areas of mathematics. So let us begin with this gentleman, no less than a Fields medalist, Manjul Bhargava, is a professor at Princeton University, and he is also an adjunct professor at TIFR and IIT Bombay. I happened to meet him several times. He's one of the fantastic, nice gentlemen that I know. Very down to earth, very simple tone, and very, very Indian, if you know what the Indianness means, in spite of the fact that he was born and brought up in USA and Canada. So this gentleman, in one of his lectures, one of his, this was Times of India, Kolkata. He was interviewed, and this is what he said. Students in India should be taught about the great ancient Indian mathematicians like Panini, Pingala, Hemachandra, Aryabhata, Bhaskara. Their stories and works inspired me. And I think they would inspire students across India. You know, those who might be at the other side of the screen, since I don't know the composition of the audience, if there are people who outside from mathematics domain, I must mention for them that Fields Medal happens to be the highest international accolade for mathematics. There is no Nobel Prize in mathematics, and many reckon Fields Medal, which is given every 4 years at ICM, International Congress of Mathematicians, and to a person who is below 40 years of age. So this is coming from a person who happens to be at the highest echelon, not of history of mathematics, but of mathematics per se. And these words are coming out of him. Many of these words were written in Indian language in beautiful poetry and contain important breakthroughs in the history of mathematics, not just ordinary mathematics. What Manjul says and what Manjul believes, that these work contain important breakthroughs coming from a Fields medalist, my friend. And he names these people: Panini, Pingala, Hemachandra. I'm sure Aryabhata or Bhaskara may be more common to general people in India, educated mass in India, but Panini, if the name is known, it is known in the context of Sanskrit grammar. Pingala perhaps is not that much known. He is a prosodist. So how come these names are included in the list of a mathematician by one of the greatest mathematicians of the present time? So this is what we would like to explore a little bit, to see what kind of work these people have done, why they are being put in the same row of names with other mathematicians like Aryabhata and Bhaskara. Here Bhaskara, of course, means Bhaskara II, the Bhaskaracharya. And in another such interview, he was asked to talk about 5 most influential book in his life. And this was his list. Shulva Sutra by Bodhayana. My junior friend Krishnendu already pointed out in his brief but very apt introduction about this Shulva Sutra. So it goes back 800 BC, and perhaps the first place where Pythagorean theorem comes up. We'll try to take it in more details and analyze this claim that in what sense Pythagorean theorem is found in Shulva Sutra. Mind you, this is at least 300 years before Pythagoras' time. Just learning geometry there is an artistic way, in something that I think India should bring back. Okay, that's controversial, whether India should bring it back or not. I'm not getting into that, but at least, again, referring to what very beautifully said by Krishnendu, that due credit must be given to the originator of certain things. It doesn't mean that the claim is made that I have to go back to that stage and learn everything from that perspective only. The world has, advanced in 2000 years, no doubt about that. No doubt that the modern mathematics has done wonder, modern science has done wonder. But it doesn't mean that when you talk about penicillin, you should never name Alexander Fleming for that. That is not the right way of doing, and that has been done repeatedly in India throughout the years, even after the 75 years of independence. We really don't know what exactly used to be there in ancient India. Either there are tall, baseless claims which are baseless in the sense that they are not being supported with enough document or enough arguments, or else we read the history that is written by foreigners who used to believe and who are indoctrinated in that particular Eurocentric pattern for their own philosophical and political, socio-political belief that there could not have been anything in these colonies, these countries like India. The second book he prefers is Chanda Sutra by Pingala. It's in 2nd or 3rd century BC. Is one of the book we are very fortunate to still have. Most of the books, ancient scriptures, are not extant. This one is there. This one is still there, and this is actually taught in the Sanskrit master's level as one of the general topic of Chanda Shastra, the prosodical analysis. The 8th chapter of this book, it contains wonderful mathematics, and that also leads to, among many other things, the idea of Fibonacci sequence. I'll just try to, elucidate a little bit on these. And then comes the Ashtadhyayi of Panini. Yes, he was a linguist, he was a grammarian, but not in the sense of the grammar textbooks that we get in our class 9, 10th, 11th standard. It was an analysis, out and out mathematical in nature, analysis of grammar of a subject, presentation of a subject existing knowledge, and its analytic way of looking at it. It's 100% mathematical in presentation and philosophy. That's how he is being treated as a mathematician, because the spirit of his grammatical work is very much mathematical in nature. And then comes the 2 other books, The Man Who Knew Infinity, the famous biography of Ramanujan, which Somnath was pointing out. I had the great fortune of translating it into Bengali, commissioned by the government of India, but that's a different story, not relevant to today's lecture. And there is a last one which I'm not getting into. So before I start talking about the basic topic today, let me give you another, point which is very important to appreciate and understand, that while talk about India in antiquity, this India is not the geographical location of India that we look today in our map. When ancient India and its mathematics or scientific achievements are referred to, it is the landmass of the whole subcontinent, right from what is now known as Pakistan, Afghanistan to in the right that Burma, Myanmar, and all these other places, Cambodia, etc. The whole landmass is referred to. The knowledge repository that was there due to certain, common culture, spread of Buddhism, and many other important things. So this could you, somebody please talking, could you please, your microphone is disturbing us. I don't know who is talking with microphone on. Could you please? Okay, so this is the Indian whole subcontinent. That is the frame of reference of the lecture today. And these are certain ruins. It is important to know, because it's a common question. There have been so many things in India. So where have they gone? Why are not these things here? Why could not India continue to excel in the domain of knowledge if really it had been there at a certain point of time? See, these ruins and the geographical location of these ruins of centers of learning, just 1, 2, 3 I have, there are so many others. There is a very fantastic pattern. If you just look at the geographical location and the time of decline of all this decline is essentially due to external hazards, invasions by various factors, mostly from northwestern corner of India. The oldest one that we know about is Taxila. And this is 1000 BC, mind you, 1000 years before Christ. This center of learning prospered in a place which is now somewhere in, it's in Pakistan, Afghanistan border. This place is called Gandhara region at that point of time. Again and again plundered by the Huns till 5th century CE, when it was completely demolished. And that point, that northwestern junction point, was the kind of bottleneck through which all these foreign invasions, before the time of Vasco da Gama and people, they came through Kerala coast. Before that, all such invasions, they used to come to that point of time. So once that was demolished, you see, after that, the learning center that prospered in somewhere around middle India, central India or some eastwardly places like Nalanda, Vikramshila. And if you just keep on looking at them, they are getting plundered again by the foreign invasion. And then these knowledge centers, you will see gradually they are shifting the other side of the Vindhya mountains. Vindhya was something standing in the midway of India, and not even Alexander could cross it. So suppose it was a kind of assurance that you get it beyond Vindhya, then perhaps you are safe. And you see, the knowledge and the culture of knowledge generation, it can never prosper until and unless there is a stability, political stability and patronization by the power of the king, power of the country, power of the state. It has to back this. It has to patronize this. Only then such a thing can prosper. So whenever there is a turmoil, whenever there is plundering by this kind of foreign invasion of different dimension, and these are all well-known facts in case of India, these were all actually destroyed, and things, they went the other side of Vindhyas, and it started prospering in Kerala. But unfortunate history of India tells us that the next flow of invasion in a different dimension, in a different disguise, the disguise of trade and commerce, it came through the Kerala coast. Started with Vasco da Gama, and then one after another European powers, and again those looting and destroying and demolishing and taking away all the knowledge doctrines from India and depositing it in Europe. Even today in Vatican Library, you will find thousands of Indian manuscript, not even catalogued. It's not known what kind of Indian knowledge repository is lying there. Because these are all in ancient time, in that particular time, that particular language, that particular way of, one particular such manuscript may require one person's whole life work to actually try and understand what exactly is there. It's not necessarily on mathematics. It's on many different subjects, but on knowledge as a whole. And of course, mathematics is there directly or indirectly, tacitly. In the socio-cultural representation, often we find out mathematical reference that leads us to tell that, yes, if the society knows this expression, then that society used to understand the corresponding knowledge of mathematics as a whole. A very simple example I can give you. When you read Vasavadatta by Shubandhu, well, it's not a mathematical text, it's a drama. But in that drama, you had a reference to Shunya as a Vindu. That's a completely different metaphor. The writer, Shubandhu, is talking about a situation where the queen, he is waiting in his palace in the night sky. The king is not around, and she was thinking about him and looking at the sky unmindfully. And she just came out with this thought that as if the god himself, with the moon as a chalk, reckoned the stars as the dot in the sky. The exact Sanskrit word being Shunya Vindavaha. The Shunya, the concept of zero, is represented by a bindu or dot in a text which is nothing, which has got nothing to do with mathematics directly. But this cultural representation, see, such a book is written for the mass. And if the general public for which the book is written can understand this correspondence and allegory that Shunya be represented by dot, then you must be able to infer from that this is a society where Shunya was already conversant with, and the knowledge of Shunya, the representation of Shunya was perhaps done by a dot mark. So not necessarily you have to get hold of mathematical scripts only. All this ancient knowledge must be explored properly and categorically catalogued and found out. It's a huge task. Anyway, so that's a way of looking at the fact that why India could not sustain with its huge repository of knowledge that once actually were created, nurtured, advanced in this great land. So if I make a list, of these, it's a small and utterly incomplete list, but I just want to put some highlight on these issues, then before Ramanujan and after Ramanujan, so you make a kind of distinction. Then in BC period, you find these people, Bodhayana, Apostamba, Katyayana, the people who are known as the Shulva Sutrakar. I'll talk about Shulva Sutra a little bit. Then Panini, I have told you already, look at the time there, his book Ashtadhyayi, 5th to 7th century sometime. These are the point of time India was in oral tradition. That is another very unfortunate aspect of India, because unfortunate in the sense that other civilizations and societies, those had some way of writing out things. They have the kind of solid proof, quote unquote, what they had. Once you can decipher their writing, once you can decipher what the Mayan codices stand for, once you can decipher what the hieroglyphics stand for, you can categorically say that this exactly is written over there. So that is a knowledge of the Egyptians, and that is the knowledge of the Mayans, or similarly for Babylonians on their clay tablets. But unfortunately, it stands fact, we all know it, that Indian tradition was Sruti, and from the Guru to Shishya, it was transmitted oral tradition. So much later, India started writing, and that is exactly where there is a scope of raising one's finger when they are not very convinced about what India achieved in the time period of Sruti. There's a common way of pointing out that okay, these are all later editions. These were not there at that point of time. The people who started writing them, they have actually invented some of the thing themselves and put it against the name of the ancient seers. That is the tradition. There is one way of looking at it. There are people who look at it as it's one way of academic controversy regarding the state of affairs. But that's unfortunate state of affairs is there because of this Sruti kind of the oral tradition kind of passed in India. And then comes the idea of Bakshali manuscript, one of the earliest known mathematical document of India, written document of India. Even the time period of that is very hotly debated nowadays. There are so many questions of interrogation marks that I have given there. As you can see, 3rd or 7th or 9th different pages of Bakshali has been recently put under the C14 carbon dating test for assessing its time period by the Bodleian Library of Oxford, and the outcomes are quite amazing. There may be again immediately the Eurocentric scholars, big names, by telling Eurocentric, I am not by an iota undermining their achievement. They are all big scholars. But the fact remains that they look at the thing through one particular kind of specs. And they have immediately jumped upon the conclusion telling that it's historically untenable. And there are other school of people, other school of thoughts, scholars who are trying to assess and understand that how this different time period of a single document is possible. It's different pages written at different point of time. Maybe it's a replacement, letter replacement by, it was being, maybe it was being withered away. So someone else, some letter scribe was assigned to copy one particular page of that. This is, after all, a birch bark document, right? And it's absolutely mutilated, now kept in Oxford Bodleian Library. It's found in a place called Bakshali, which is now in Pakistan, 80 odd kilometers away from Peshawar, a place which is quite close to that ancient seat of learning, Takshila. So I'll come to that if time permits. Then you have these big names that you know, Aryabhata, Bhaskara, Brahmagupta, and word of caution there, this gentleman is Aryabhata, not Aryabhatta. Vatta is a complete different thing. If you go by the name, the reason of Vatta and Vata, there's different clans. His book is Aryabhatiya. So as a great Aryabhata, and then Bhaskara I, the commentator of Aryabhata, Brahmagupta, the great mathematician, one of the greatest. Even in Manjul Bhargav's lecture on its Fields Medal, he refers to mathematics of Brahmagupta. He proudly says that what I am doing today has begun at the time of Brahmagupta. Gauss generalized it, and then I am doing further work on it. I myself have heard that lecture. So this is the level of mathematics that these people have done. My friends, one must understand that history of mathematics does not mean the usual history course that you study in your class 9th and 10th standard, where you have to learn by heart the year when Babar did that and when Akbar did that. That is not what history of mathematics is all about. It's 80% mathematics. You have to understand the mathematics done by these people, and you have to translate in the language of modern mathematics to see, to compare that what huge achievements they have made. And of course, then you have to find that what were the falterings, what were the impediments, where have they stuck, where have they got stuck. So that's the analysis which is known as history of mathematics per se. And there's absolutely no reason why a course on history of mathematics should not be made compulsory in every mathematics master's degree that is given in any institute of India. We are not talking about giving the whole course of history of mathematics. That may be a separate thing to pursue. Of course, more than enough material is there. But at least a general selected course on history of mathematics should be there for every master's degree holder should know that what is the country he is belonging to, what is the past mathematical achievements of it, not to reside in the past, but to know and get yourself, the thrill and the motivation that these are the people whose genes are flowing, whose blood is flowing in my body as well. That motivates a person to achieve more. If not anything else, this must be the reason. Anyway, that's a separate issue altogether. So coming back to this, there is a list, as you can see, perhaps the Kerala school that I pointed out the other side of the Vindhya in the river, by the river Nila. This Narayan Pandita and then Madhava, the Guru Madhava has been referred to by many of his disciples, as you can see their names, though unfortunately none of the original work of Madhava is extant. This Venuvaraha and Sfuta Chandrapti, none of these is available, perhaps lost for, I don't know, maybe somebody someday will find a copy of that. But till now it is only referred by other later scholars that in terms of these books that we came to know from our Guru Madhava, this, that, etc. These are people like Jeshta Deva, Shankar Warrior, and so on. So it's a huge repository, and this Kerala school has done tremendous mathematics, which is very close to modern mathematics, astounding amount of mathematics. In fact, nowadays, this tan inverse series of expansion, that is now referred to as Madhava-Gregory series. Just like there is a claim that Fibonacci number, Fibonacci sequence should be called Virahanka Fibonacci or Hemachandra Fibonacci sequence, because these people have done this same thing much earlier. And that history repeats itself kind of thing has happened again and again with Indian achievements of mathematics, and much later kind of, doing exactly the same thing, just like, what Europe has done in 17th century. You just go a kind of flashback some 1200, 600, 800 years back in India, you'll see the exact same thing happening. Even I can show you example, I can cite you example in terms of exact same equation, exact same problem is being unearthed again and done afresh. Now there is a question of controversy, whether it was done afresh, whether these somehow reached Europe and the people, they just learned by heart and translated it, claiming that it is their own work or not. These are all matter of controversy. I'm not getting into that. There can be difference of opinion, but the fact remains that whatever India has achieved in the time of say 7th century, 8th century, 9th century, Brahmagupta and others, it has been just like replayed, just like you have action replay. There's a kind of action replay of this mathematics that happened in 16th, 17th century Europe. If time permits, I'll just take you through. So, contribution of India to mathematics, if you want to talk about that, no such talk can, take place without a reference to this decimal place value system in tandem with zero. That perhaps is the greatest contribution to modern mathematics by India, numeral. This idea of zero was there in many other civilizations also. But that was as a kind of symbol somewhere as a kind of nothingness, somewhere, these are kind of, they never bloomed into the full potential of one numeral on which mathematics can be done. So that happened only in India. But this itself is such a huge topic of discussion. So I can talk about 3-4 hours right on this particular topic, which I have done again and again in various places. So today is not right time for that. I will not stand on zero. I'll just refer to it, just point it out and pass on. I'll give you some reference if you are interested to look into, to know it at a greater details if you are not already aware of that. And then we'll pass on to some other more important issues, because this issue of zero, it's like it's like a sun in the sky. When the sun is there in the sky, you don't see any other stars or moons. So other achievements, other Indian achievements, excellent as they were, are like shadowed by the presence of this sun. The concept of zero, it is such a fundamental, such a paramount, such a concept of paramount importance. Okay, so this my friend, I think, who told about it, this Somnath Da, perhaps. Yes, this is in the ICM, International Congress of Mathematicians, that is held after every 4 years. 2010 is the only time it was there in India. I was fortunate to be there. And this is one of the official poster where this particular sloka from Vedanga Jyotish. Vedanga, Veda has 6 limbs: Shiksha, Kalpa, Vyakarana, Nirukta, Chanda, and Jyotish, of which Chanda is the one which is mathematically important, as I have already pointed out about Pingala's Chanda Sutra. The other one is Jyotisha. Now, this Jyotisha does not mean the astrology. This Jyotish refers to astronomy, the time calculation, calendrics. And this Vedanga Jyotish has this particular fantastic reference to mathematics that has already been pointed out by Somnath Da. I'm not getting into that any further. And before I proceed further, I would like to, talking about so many serious things, so I'd like to share with you this interesting anecdote. This is a kind of joke that I got in, actually my elder daughter supplied me with this particular joke from Facebook, that since I talk about zero so many times, what happens to my family member when I start talking about zero, you can well imagine that. So one day my elder daughter gave me this, that this is what I find in Facebook. And you see, I laughed at it, as you will, but I had a little bit of, I'll come to that once I share the joke with you. It says that, this is the imaginative past of Aryabhata in front of Ayuka in the Pune. It's a popular joke in social media. It shares like this here. It says, one day Aryabhata asked his wife, "Will you allow me to spend the night out with my friends?" And the wife says, "According to your calculation, you are a great mathematician, so you can calculate yourself. What is the probability of my giving consent to this?" And it is then Aryabhata invented zero. So I don't know what you are. Maybe you are also smiling or laughing. When I used to present this in front of an audience that I can see, people used to burst in laughter. But then I find it's really pity that people even make a joke out of something which is out and out wrong information. Aryabhata never invented zero. Aryabhata used zero. But at least 700 years before Aryabhata, I can show you precise and to-the-point reference of zero as a numeral, as a number in Pingala Chanda Sutra. In the 8th chapter, the 4 sutras that are there leading to a combinatorial algorithm, there's specific reference to Rupe Shunyam and Di Shunne. And these Shunna referred to there happens to be clear-cut mathematical zero. Of course, again, in terms of language, we don't know what exactly this Shunna used to look like. How do they used to write this Shunna? That we don't know. But that this zero is a mathematical zero is quite clear and quite appreciable, because the whole calculation by these 4 sutras, of which 2 I have uttered, is a mathematical calculation pertaining to a combinatorial one. So if time permits, maybe I'll come to that later on. So this is the state of, unfortunate and sorry state of affair as far as I understand it, that we cut a joke, but even that joke stands on a wrong historical information that is wrong, not just a European's perspective, but the perspective of an Indian. We Indians should at least know what is there in India, what was there in India categorically. Of course, it is a free world. It's a free world of academics. You have your own way. You have every right to make your observations, to protest to something, to write your, you have your own point of view, which is contradictory to others. That is all welcome. But you should not suppress facts. The facts should be there. And then you are welcome to come and contradict the fact, to have an alternative proposal, have an alternative way of looking at it. That's most welcome. People are ready to, discuss always. That's the beauty of the academic fraternity. But you should not suppress fact to establish your claims, the claims that has already been sort of pre-decided, your biased position out of your socio-economic or political need, the biased position that actually motivates you to make some claim and to fulfill this, to accomplish this aspiration. You are suppressing certain things or distorting certain things. That is not acceptable. Well, many things this gentleman Aryabhatta did, but he didn't invent zero. His beautiful work involving the square root and cube root calculations, it's impossible without a solid understanding of zero. What he did in his own way, it's Patapayadi system. Again, that is something very technical, and I'll take hours if I want to get into that in details. But because I named Aryabhatta, I just will stand on one particular sloka from Aryabhatta, telling you that what level of intellect these people had. You see, this is the time when, the fire altars were of tremendous importance to this society. They used to believe that you can attain certain spiritual goals by giving this yagga and other things. And the shape of these altars were very important. These three shapes that you can see perhaps in front of you in the picture that I'm trying to show you. One is circular, one is semicircular, one is square. And for some ritual purpose, it was necessary that they should have equal area. So converting one area into the other, that's a purely mathematical, purely geometrical problem. But that actually came to India. Indian geometry, it prospered due to this kind of things. Just like Greek geometry, you go back to Egypt. Greek geometry is coming from Egypt, and that geometry prospered due to the inundation of Nile, recurrent inundation, and measurement of their lands, etc. Indian geometry prospered out of the need of this Yagga Vedi, the fire altars. Now, these are three kind of fires that are to be, considered. One is called Dakshinagni, Garhapatta Agni, and Avhani Agni. And for these three types of, altars are to be made. And this actually paved the path of relevant mathematical calculation. In Aryabhatta, you get this sloka that you can see in front. In Sanskrit, it says, Chaturadhikam, Shatamashtagunam, Dvashashtistatha Sahasranam, Ojutadaya Vishkambhasa, Ashanno Britta Parinaha. Now, this is one most difficult impediment for us, general people, to follow the ancient Indian texts in mathematics or any science, that these are all written in Sanskrit. And somehow Sanskrit is not being taught anymore in general. We don't know about it. But you see, it's not difficult if you want to understand. I don't understand. By no means and standard I am a Sanskritist, not an iota of it. But even I can understand it. These days, if you want to understand, there are online dictionaries. There are people who are at the know. You can consult them, and just you should want to know it. That's the first and foremost thing. And then you can very easily decipher, because after all, the language we all speak, they are derivative of Sanskrit. Most of us. I'm not talking about the South Indian languages. They are not Dravid languages are of different origin, but this Bengali, Oriya, and all other local languages, Hindi, everything comes from Sanskrit. So it's not very difficult if you want to follow. Like here, Chaturadhikam. Chatura is 4, Adhik is more. How much more? Shatam. So Chaturadhikam Shatam, as you can see here, 100 plus 4. And then Ashtogunam. So you are multiplying that by 8. And then Dvashashtis Tatha Sahasranam. Dvashashti, Shashti is 60. Dvashashti is 62. Sahasranam. So that's 6,200. 1,000, I'm sorry. So this is the number you are talking about. 100 plus 4 times 8 added with 62,000. What about this number? The second line says that this number represents something which is Ojutodaya Vishkam Bhasha. Ojuta is 10,000. So Ojutodaya is 20,000. And Vishkamva is diameter. So you are talking about a circle with diameter 20,000 unit. And what is this numeral on top? It is Ashanno Britta Parinaha. So Britta is a circle. Of course, Parinaha is the so-called length of the circle, the circumference. So the length of this circle that has 20,000 units as its diameter is given by this number, 100 plus 4 into 8 plus 62,000. What is so beautiful in it? 2 points. First of all, you divide by that. So just as I told you already, you want to appreciate that, you translate it in your modern language. Now everybody knows that 2 pi r is the circumference. R, 2r is the diameter. So here 2r is 20,000. Ojutodaya Viskam Bhasha. And you know this value of 2 pi r. The whole value is given there in numerals. So 2 pi r divided by 2r, what you are getting at? You are getting at pi. So do that division here. And bingo, you get that value, 3.1416. And that is Aryabhata. More than that, he says, as I have pointed out in red, I took this slide from one of my good friend, Krishnamurti Ram Subramaniam of IIT Mumbai. You see there? It's red. It's marked red. Ashanno. You won't get the exact value. It's an approximation. Even that much was understood. That you cannot get exact decimal value of pi. It's Ashanno Britta Parinaha. And that is the level of mathematics these people has reached to. When you talk about ancient India, you must bear such things in your mind. And then if you are interested in knowing about, natural history of evolution of zero, this is what one reference that I can give you. This is in IIT Gandhinagar 2017, an international conference. This is a 1-hour lecture available in net. You just go and type my name in Parthasarathi Mukhopadhyay in what is that called? YouTube. And you will find this lecture if you are interested. It's in English. If you want to read it in Bengali, again, this is a reference. This is in the site www.bigyan.org.in. Bigyan is spelled in this way for the reason known to the people who run the site. There are 2 separate parts in which I have written a detailed, more or less detailed story of this evolution of zero as a numeral across several civilizations. So if you want to read it in Bengali, this is one reference for you. And then finally, a few months back, this is what we have installed in our college, commemorating our Diamond Jubilee. This is the Zero Gallery, where you can come. You are most welcome to come and visit the Zero Gallery of Ramakrishna Mission Residential College, Narendrapur, where all this history of evolution of zero across all the ancient civilizations. In what sense we say that zero is invented in India? It's an invention. It's not a discovery. It had to be invented. So what was prior to that? What about the other civilizations? Didn't they have their own zeros? If yes, then why that zero is not accepted as the progenitor of the modern mathematical zero? What's the deficiency? If they didn't have zero, then how could they manage to calculate? Well, if that was a way of calculation, then why do we need zero at all? All these are very pertinent questions on which one can go on talking for hours. And this gallery is showcasing, it's trying to showcase the whole story on which we are right now making a half-an-hour documentary, which will be available, I believe, by the end of this month in YouTube, that will focus the purpose of this gallery. But you are most welcome to come and visit this gallery physically. Due to pandemic time, unfortunately, everything is stalled. So is the gallery. It was inaugurated 6th of March this year by the director of Indian Statistical Institute, Professor Shanghamitra Bandyopadhyay, and also accompanied by Professor Ashish Chatterjee, the Vice Chancellor of Calcutta University, Pro-VC Academic. But unfortunately, right from that day onward, this is generally put under lock and key because of the pandemic situation. But let us expect that pandemic will be over now, sooner or later. And then allow me to extend my, heartiest welcome to all of you to come and visit this gallery. And there are these 2 books also. If you are interested, these are actually supplementary materials to this gallery telling you the story of zero. So they are available in Amazon. If you are interested, you can try to grab and go through it. That will give you a taste of what zero is all about. Coming to the Shulva Sutras. Shulva means Rajju, knotted strings by which these measurements were done. There's a culture of ancient India going back at least 800 BCE, if not earlier. And these are the people, Bodhayana, Manava, Apastamba, Katyayana. These are the people whose names are related with Shulva Sutras. These are kind of manual sutras. Sutra is a kind of text aphorism. It's very cryptic in nature. It's not to be elaborated because you remember this is oral tradition. It has to be short. If you look at the definition, Vishnu Dharmattara Purana, it says that Alpaksharam, the first word of the definition of Sutra is Alpaksharam. Must be very concise. Alpa Akshara. Ashandigdham. You cannot just have some queries or question mark that maybe this, maybe that. What is the interpretation? I don't understand. No, that is not a Sutra. Alpaksharam, Ashandigdham, Sharavat, gist, Vishyato Mukham, universal. It has to be applicable everywhere and not some specific cases. Then it's not a Sutra. So look at the idea of theorem. Alpaksharam, Ashandigdham, Sharavat, Vishyato Mukham, Ostobham. There should not be any meaningless phrase. There is no scope of, literal or poetic flair, making things sounding better. No, make it sharp and small as you can, because you have to remember it and pass it on to the next generation. Ostobham, Anobaddhamcha, as unique. There cannot be two different ways of expressing the same. But these are the parameters with which you define a sutra. So these are Shulva Sutras, cryptic. You have to understand the meaning of that. You can't ask, well, nothing else is told. Yes, it was told. It was told by the gurus to their shishyas. You have to understand from the perspective. You have to look at the application of the sutras and don't ever claim that this is not being proved. These Shulva Sutrakars, they are not writing books for you. They are not writing geometry textbooks. They had no intention of giving you all the details that they knew. And because it is not there, you cannot claim, so they did not know anything. That will be stupid. So try to appreciate in face value what it is and look at the application of the successive sutras and see what it leads you to. So these are kind of, fire altars. One particular one you can see here, even till date, South India, where dogmatic people still believe in the Vedic tradition, they still adhere to this kind of things called Shane Achiti. Shane is a falcon. As you can see, this measurement of exact measurement and exact shapes of the bricks and the numbers, etc., were absolutely important to making of this. And those people, again, see, I am not preaching that this is something you must do from tomorrow onwards. No, I don't believe in these things myself. Let that be very clear. What I am interested is this, that these people at that point of time believed that these constructions, the perfection of this construction was of paramount importance for achieving their goal, because they believed that only this perfect construction of an altar on which you sit and give your offering, then this goal will be achieved. Had it not been so, has it been some kind of casual, then this would never have prospered to these finest details. That's the mathematical or scientific importance of this culture, that they believed in perfection of this kind of things. That is why geometry prospered. That's my point. Not that from tomorrow onwards, you should try to mimic all such things. That's your business. That's absolutely your business. If you think you should mimic, you are most welcome. I at least have no objection to it. But don't ask me to mimic that, because I don't like that. That's perfectly legitimate and okay. It's not a kind of dogma. But you want to know what is what, then you must know it from the perspective. Why did it prosper? Why suddenly Shulva Sutras become important? Because of this, so many constructions had to be done. And this required in-depth knowledge of geometry, much earlier than Euclid. Euclid is 3rd century BC. Pythagoras, 5th century BC. This at least 8th century BC. to begin with. Even before that, we don't know. Are they just something age-old and nobody is bothering about it? No, no, no. Nobody perhaps is bothering about it in India. We don't bother. Europeans bother. Americans bother. They talk about Indology. They look at this civilization as an ancient, great civilization, a repository of ancient knowledge, many of which are still not known, have been still unearthed. But we look at them with a kind of, highbrow. There's nothing there, absolute nonsense. This is a book written in 2016, a full-scale book by a French historian of mathematics, an expert on Shulva Sutra. As you can see the name, Jean-Michel Delire. Les mathématiques de l'hôtel védique, le Bodha and Shulva Sutra et son commentaire Shulva Dipika. Bodha and Shulva Sutra and its commentary Shulva Dipika. And there is one gentleman, Michel Danino, who is in IIT Gandhinagar. He's an adjunct professor there and a recipient of Padma Shri. One of the foremost historians of mathematics, particularly ancient Indian mathematics. Michel reviewed the book in 2018, and this is the language from his review. In a long discussion on the so-called Pythagorean theorem, which Bodhayana expressed differently as the property of a diagonal of a rectangle rather than hypotenuse of a right angle triangle, both with specific dimension and in general formulation, Delire makes a praiseworthy attempt to grasp the Shulva Sutras on their own terms rather than through the prism of other Greek or modern approach. That's most important. Rather than through the prism of others, look at it as it is, try to appreciate and understand what it means. And what do I see here? This is the particular sutra under consideration. Dirgha chaturasya akshanaya rajju parshvamani tirjangmani cha jat prithak bhute kuruta samubhayam karati. What does it mean? Let us try to decipher. Because it's Sanskrit, I know most of you are not conversant. So let us just try to break it up. Dirgha chaturasra. Chaturasra is a quadrilateral. Dirgha chaturasra, because of course one side is dirgha than the other. It's a rectangle, right? And you can see in front of you. And I must thank my good friend Amartya Datta, IESI Kolkata. He's a very good friend of mine. He has shared some of his slides with me. These diagrams of Shulva Sutra that I am showing you, and I will be showing in next few slides, are due to Amartya. So my sincere thanks to him. And here you see this. I just repeat again, Dirgha Chaturasra. So that's a rectangle that is being referred to. And in modern notation, I name it ABCD, as you can see in front of you. Akshanaya Rajju. So Akshanaya Rajju is the diagonal. It means diagonal. So you can see the diagonal BD. Now look at the word Parshvamani and Tirjangmani. So Parshva is side. Very simple. Parshva. Tirjangmani, that's the lateral side. Tirjak. So lateral side means, so basically you're talking about length and breadth. The way we usually name the sides of a rectangle. So Parshvamani and Tirjangmani chat prithak bhute kuruta. So separately whatever they do, these two sides, AB and AD. The Akshanaya Rajju alone, tamu bhayam karoti. It does what they two separately does. This Akshanaya Rajju alone does the same thing. That's the rule. Now you say that it's Pythagorean theorem. And of course, the first objection is, well, it is not telling at all what they are supposed to do. It says that they do something. Kuruta. What they do? They prithak bhute kuruta samubhayam karoti. It does the same, but does what? Well, it's not there. It's not there. Then why should you accept it as a Pythagorean theorem? Why should you accept that it is actually telling that the square on AB plus square on AD is equal to square on BD? We won't accept it. No problem. This is Sutra 48. Now go to Sutra 49. The very next one in the same book, same text. Bodha and Shulva Sutra number 50. What does it tell? It's an application of the previous sutra. And now you see what it is applying, what it is doing. It says Nana Chaturasre Shamashan Karanya Kanyasa Karanya Borshiyasha Bridham Ulikhet Bridhrasha Akshanayaraju Shamastayo Parshomani Bhavati. So again, let us try to analyze the words and try to make sense out of it. If you want to go by English, the interpretation is written there. But I would like you to take word by word through the meaning. Otherwise, you may think, oh, that's what you are claiming. Who knows the meaning? So try word by word. Nana Chaturasre. Chaturasra we already know. I mean, it's a quadrilateral. So these are two. The Shamusha, the problem is Nana Chaturasre. Shamushan. The problem is to amalgamate two different squares into one. Not by mensuration, by pure geometry. You are given two different squares. If you look at the diagram, ABCD is a square. Can you see that? Here, follow me. A, B, C, D. Suppose this is a square. There's another square is this ICGH. Two different squares. Nana Chaturasre Shamushwan. Now, what is the problem? The problem is to find out, to construct a new square whose area will be equal to the sum of these two. And this is the rule for that. What is the rule? Kanyasa Karanya. Kanyasa is the smaller one. Karanya means to mark off, to cut off. So, you have to cut off the smaller one. That means the side of the smaller one, the length of the smaller side. You have to cut off this. Cut off from whom? Borshiyasha Bridhram. From the larger one, its side, you cut off the length of the smaller one. So that's what I am doing here. I am cutting off BE equal to CG. Clear? And then you get an augmented figure there. So you augment that. One side is already AB. You have cut off a new side that is BE. And then you augment and complete this figure. Ullikhet Bridhrasya. This augmented figure, it's Akshanaya Rajju. That is the diagonal. The diagonal of this augmented figure. Shamastayo Parshomani Bhavati. It becomes the side of the total thing. The amalgamation that you want, the side of this amalgamated figure is given by the Akshanaya Rajju of this augmented figure here. So now what do you see? Now what do you see? You see clear enunciation of AB square plus BE squared is equal to AE squared. Do you accept it? Initial square was ABCD, the side is AB square. So you have this AB here. CG is the side of the other square with which you have taken this BE equal, cut it off, and then you make it this. And that's where you go back to the previous sutra. Now you have a rectangle. And this is the Akshanaya Rajju. And now you know by virtue of the previous one that Parshomani Tirjangmani cha jat prithak bhute kuruta, this Akshanaya Rajju tanu bhayam karoti. So this Akshanaya Rajju, A squared, is equal to AB squared plus B squared. It's a pure and simple geometric construction. No number involved, no mensuration. Not that you know the length and you make the sum of the square, simplify and take the square root of that numerically and find out the length. No, it's a pure geometry that is being done. That's Shulva Sutra. I give some other example. More involved. It's in Kattaya. Javat pramanani shamochaturasranne ki kartum chikirsha dekonani tani bhavanti tirjaka digunanne kata ekadhikani trayostrir bhavati tasheshu stat karoti. Again, let us go word by word and try to find out the beautiful meaning of it. Yavat. Now this word Yavat was used in ancient Indian mathematics as a kind of unknown, any arbitrary number. Yavat or Yavat Tavat, like we use the unknown number n. So suppose Yavat Pramanani Shamo Chaturasranne ki kartum. So what is the problem here? The problem is the pramanani shamochaturasranne ki kartum. Eki kartum means ekotrikaran. That is amalgamation. You have to add, sum up. What? Unknown number, that is an arbitrary number of shamochaturasra, that is square, is given to you. But all of them of equal size now. Unlike the previous one. Previous one, they were nana chaturasra, different. Now this is shamochaturasra pramanani, all of them same size. So you have some, for our understanding in the modern language, suppose you have n number of squares, each with side length a. So what is the problem? What do you want to do? You want to amalgamate all of them and make one single large square. The question is, what will be the side of that? You have to solve it geometrically. If you go by the modern understanding of mensuration, it is absolutely simple. Total area is n times a squared. So the required length that you would like to have is root over n into a. As simple as that. But here, the problem for this Kattayan was to get hold of this exactly by geometry. And you see, that's very important. Only geometry can get hold of the exact length. You go by numerals, the length become irrational. You can never exactly calculate, exactly phrase it out. What exactly is the length? Just like root 2 is fine. But root 2 in terms of decimals is not fine. 1.41 to something and then 3 dots. And that 3 dot, the ellipsis, is a dangerous thing in mathematics. It says that you can never stop. Go on forever. But certainly you can draw what is root 2, the length, exactly. Get hold of the square of side 1 and draw its diagonal. It's exactly root 2. Whatever that length is, that is root 2. No approximation involved. Approximation comes when you want to find the value of root 2 in decimal expression. So root 2 is not an approximate number. Decimal representation of root 2 is an approximate number. And that comes when you do geometry in terms of number. That's mensuration. These people are not doing that. They are doing exact calculations. That's a subtle difference and an absolutely important difference that must be understood. Exact calculations are being done geometrically. And how do he propose? He proposes to do this calculation in this beautiful manner. Look at the sutras, my friend. So I start again. I have n number of squares, each with side a in our modern language. And I want to make one single square whose area will be equal to the total area of these n squares. And the sutra says, come here, Chikirsha dekonani tani bhavanti tirjata. So what is chikirsha? It's desire. Whatever you desire, there's a desired number, that number n. The number n that is given to you. That desired number of squares that is given to you. Chikirshad ek unani. Uno is less. Ek unani means one less than that number. So the number was n. You are talking about n minus 1 times a. Chikirshad ekonani tani. That's the number n minus 1 into a. And that becomes the tirjaka, transverse side. That length, n minus 1 into a, is a transverse side. Of what? Of what? Okay, look here. There's a word, traya. There's a word here, traya srir bhavati. So traya refers to that triangle. What kind of triangle? The triangle that looks like srika. Srika means arrowhead. And how does an arrowhead look like? It's an isosceles triangle. So it's an isosceles triangle of which the transverse side is chikirsha dekonani tani bhavanti tirjaka. The transverse side is n minus 1 into a. There's an unequal side. What about the other two sides? That is given here. Digunanne kata ekadhikani. Ek adhikani, that was ek unani, n minus 1 into a. This is ek adhikani, n plus 1 into a. But this n plus 1 into a is not one side. It is that sum total of the two sides. Digunanne kata, ekata, in totality, ekatrita. both sides in total is twice as much. So each side will be half of that. So this isosceles triangle, its base is n minus 1 into a, and the other two equal sides are n plus 1 into a by 2. That constructs your Srika, the arrow formation. And how is this arrow appreciated? What controls this nature of an isosceles triangle? Its height. The whole construction refers to the height of this. Tasheshu statkaruti. The height of this will give you the required length. Once you make this construction with this unknown number, whatever that n is, chikirsha dekonani tani bhavanti tirjaka, and the other two sides, digunannekata ekadhikani, and by means of this you make this arrowhead, trayosrir bhavati, and in that srika, which is determined by its height, that is what you are after. Tasheshu statkaroti. And look at the beautiful, beautiful appreciation and understanding of Pythagorean theorem. In modern language, what you are talking about, my friends? You are talking about n plus 1 into a by 2 whole square minus n minus 1 into a by 2 whole square is equal to n s squared. This side, whole side is n minus 1 into a. So you know the isosceles triangle, the height, the perpendicular, it divides the base in two equal parts. So half of this is actually n minus 1 into a by 2. So now you look at this triangle. If you want to calculate the height, this is hypotenuse square minus this square, and that gives you this root n into a, the length. The length that is required. Mensuration has already confirmed you from your modern perspective that this must be the length that you are after. And they are reaching it by pure geometry, driven by, behind the curtain, these beautiful algebraic results. These results are algebraic results. N plus 1 into a by 2. This is class 7 or 8 algebra, right? N plus 1 into a by 2 whole square minus n minus 1 into a by 2 whole square is equal to n squared. Now, they didn't do it algebra. They didn't do this symbolism. They didn't talk about the formula. But the geometry is actually driven, perhaps at their level unknowingly, behind the curtain, but driven by the algebraic spirit. Look at one more before I switch over to some other topic. This is the construction of a square equal in area to a given rectangle. This is the construction of a square equal in area to a given rectangle, right? I think everybody here has done this at some point of time in school days, right? It is still taught in class 9 or 10. In my days, it was a very common question of Madhyamik exam to construct a square equal in area to a given rectangle. And this is what has been done by Bodhayan. That's Sutra number 54. We talked about 49, 50. This is 54. And before I get into the details of the Sutra, just read these 3-4 lines that this gentleman Seidenberg, who was a historian of mathematics, and this is the famous book of 1978, The Origin of Mathematics. And Seidenberg says, this is entirely in the spirit of the elements of Euclid, book 2. Indeed, I would say it's more in the spirit of book 2 than book 2 itself. This done by Bodhayan 300 years, 500 years before Euclid at least. And he is telling that this is more in the spirit of Euclid than Euclid himself. And everybody says all around the world that geometry is due to Greeks and Euclid is the father of plane geometry. What exactly is happening here? What are these? Where have they gone? And this Seidenberg, in 1978, when he is writing this, there's no reason to believe that he is a kind of, a member of certain Indian political party. No. He's not Indian. He is doing research and writing fantastic books. If you're interested, go and read the book. You'll find his opinion. So look at the construction. It's a fantastic construction. A square equal in area to a rectangle. Again, Dirgha Chaturasra Now, by now, my friends, those who are listening, the other side of it, it's a pity that I can't see you. That's what we miss nowadays. Can't have eye contact with my audience. It's very difficult to motivate oneself when he's a speaker until and unless he can see his audience appreciating or rejecting whatever. Both is welcome to modify my own way of delivering. But unfortunately, these days that has gone completely missing. So I just take it as an axiom that perhaps some of you at the other end are listening to it carefully, trying to follow me. For them, it is not new now. Dirgha chaturasrang, shamo chaturasrang. These words are known now. Dirgha chatura as a rectangle. Shamo chaturasrang, a square. Chikirshang. So that's what you desire. You want to convert a Dirgha chatura into a Shamo chatura. That's what the problem is. Constructing a square equal in area to a given rectangle. And again, my friends, by geometry, exact construction, no approximation involved. And what is the sutra for that? Stirjangamaning, see, Chikirshang, Stirjangamaning Karaning Kritva. So, again, that word is already known to us, Stirjangamaning, the transverse side. Take the rectangle. So, in the language of modern figure, this A, B, C, D that we have drawn over here, the side is AD, the Stirjangamaning, the breadth, the smaller one. It has to be Karaning Kritva. You know, Karani, this is also known already. Karani is to cut off, mark off. So to mark it off. Of course, mark off from what? The other one, the larger one. So from the length, you cut off the side equal to breadth. That means you cut off this AE. You get the point E here, right? AE equals to AD. So that's Tirjangmaning Karaning Kritva. Next. Shesham Didha Vibhajya. Shesham. Residue. Remainder. So after you cut it off, AE from this length, what is left? This much. The rest of the length is left. That is Shesham, and you divide it into equal parts. Didha Vibhajya. 2 parts, equal. And you get this point G over here, right? So that's the point here. You get this point G. Shesham Didha Vibhajya. And then, well, there's a large, long Sanskrit word. That's the impediment with Sanskrit for people like me who doesn't know it. You have to break it up, right? Viparjashe taruchya padadhyat. It means actually viparjashe itarat cha upodadhyat. So break it up and try to understand the meaning phrase by phrase, word by word. So viparjashe means once you reach this point of construction, you will get this G here. So you had this equal to B, and then rest is of course A minus B. A is the length, suppose. For us in our modern language, length is A and the breadth is B. So the rest is A minus B. You have taken the midpoint of that. So it is A minus B by 2. And now after you reach it, you go turn around, viparjashe, and progress in that direction. Itarat cha. You just turn around and progress in the opposite direction. So previously you were going from E to G to get this midpoint. Now you go back and add them up. Upodadhyat. So you add these 2 parts. This was B and this much is A minus B by 2. And once you add them, you get what? In our language, A plus B by 2. So viparjashe itarat cha upodadhyat. You got this length. And then khandam abhapena tat sampurayet tasya nirharaha utkaha. So utkaha again is what you want to have, the desired length. And how do you get hold of it? The nirharana. Tasya nirharana. What you want, utkaha, how do you get hold of it now? Tasya nirharaha utkaha. That is stated in this part. Khandam abhapena tat sampurayet. Now this, once you find this A plus B by 2, you see the initial segment you started with, there's a deficiency. Abhapa, khandam, a part. It's a part of what you need. It's deficient. And you have to complete that deficiency. Tat shampurayet. Complete it. Shampurayet. How do you do that? Mathematically, it means that you now take G as a center and draw an arc. And then you see at this point, initial point E that you got hold of here, this E. At this point of E, this EF was exactly equal to B. And now once you draw this arc with respect to this arc, this segment EF, this is Khandam. It's deficient. You have to go up to the arc. Tat Shampurayat. So just extend it to that arc. And you reach this point I, as you can see here. You reach this point I. So you get this length EI. And that is what you want. Tasya nirharaha utkaha. This is the length you are trying to find. This is the required length of the side of that square, whose area will be equal to the area of the rectangle. And once again, you see Pythagorean theorem in action. Once you have this side length, Viparjasheta Torochato Torocho Padodhyat. So that is added this to. What was that length? A plus B by 2. What is the length of this base EG? That is A minus B by 2. So then what you are talking about? The length, this height of the right angle triangle, it is A plus B by 2 whole square minus A minus B by 2 whole square. And you know it is AB. That is root AB whole square. So the length is root AB. So the length is root AB. So on this length, if you construct the square, you will get the area of the square, which is equal to the given rectangle. This is geometry. This is the level of geometry that was there prevalent in India 500 years before Euclid. These are only 3 examples. You read Shulva Sutra books. I've given you the name of those authors. Thibau to begin with, then Vibhuti Bhushan Datta, Bibi Datta, Swami Vidyaranya, as he became at a later phase of his life. You have the book of Seidenberg and many others like this Jean-Michel Delire, a very recent book, some 3 years back. You read them if you want to know what exactly is there. And then come and tell there was nothing in India. There was nothing in the ancient Vedic genre. There's no mathematics. First you should know and then you should debate. The problem is, the prevailing situation is 99.9% people who make comments in this area, they are not conversant of either side. They have their pre-decided views, dogmas given by some of the gurus of that particular doctrine, and they are only uttering that. You say something else, they will tell, do you know more than him? He is such a great person. He told that this is not there. That is the sorry state of affairs. So objective study must be done. Exactly what is what. There's no point in telling that, Ravana has a Boeing jet plane to fly Sita. Or, there was a, plastic surgery of Ganesha. It's not necessary to talk about mambo jumbo. There are things in ancient India that are really worth boasting of. Those are real great things. But you should know it. You see, in that particular book of Seidenberg, what he says is categorically absolutely important. He says that, referring to Thibaut, and answering that question that I have already asked you, where has it gone, all these things? But that's another very, sarcastic question that is asked when you propose this kind of knowledge that was prevalent in ancient India. The people who are criticizing this, they often ask you, oh, everything was there, so where have they gone? This is one answer given by this non-Indian person. Nor did he, Thibaut, formulate the obvious conclusion, namely that the Greeks were not the inventors of plane geometry. Rather, it was the Indians. At least this was the message that the Greek scholars saw in the Thibaut's paper. And they didn't like it. You remember Thibaut's paper was in 18 something. It's not today. More than 100 years old. Right at that point, Europe came to know about this beautiful geometry, but they simply suppressed it. They didn't like it. If the Indians invented plane geometry, what was to become of the Greek genius? or the Greek miracle. And most of the refutations were merely Oti dismissal. Anyway, the damage has been done. And the Shulva Sutras have never taken the position in the history of mathematics that they deserve. That's the sorry state of affairs. I just here want to quote a few lines from one of the present-day luminary, and with all my due respect to his scholarship, erudite scholarship, I have the highest form of, reverence for this Bharat Ratna Professor Amartya Sen. But when it comes to this particular point, most humbly, I beg to differ. He writes in his book, Argumentative Indian, that as it happens, despite the richness of the Vedas in many other respects, there is no sophisticated mathematics in them, nor anything that can be called rigorous science. You see, a person like Professor Sen, of his stature, the person who is so famous for his analytic description, analytic presentation of his thought, here only uses only a few words in a sentence to summarily dismiss. There is no sophisticated mathematics in them. Well, if by Vedas, what you mean is the complete Vedic genre, like these things, Shulva Sutras, of course, you won't get Shulva Sutra in the Shanghitas. Vedas, it doesn't refer to Shanghitas only. There are several layers of Veda. So these are in definitely Jajur Veda. This ritualistic practice, it's a part of that. And so if you refer to the Vedic genre of the doctrines, then certainly it is there. What else do you say? How do you write that in just one single line? This is a Oti dismissal, the kind of dismissal that Seidenberg has pointed out in 1978. And then comes the next line. There was, however, much of both in India in the first millennium CE, because it suits his theory fine. First millennium CE, it is after Alexandrian invasion. So everything that India knows now came through Greece via Alexander. That's the Eurocentric Marxist doctrine. With all my due respect to Professor Sen, I have written letters to him, emailed him in his Harvard address, very humbly asking specific questions about Pingal Chanda Sutra and Shulva Sutra. Just wanted to know, as a passionate learner, that what is his take on these two issues regarding this particular line of his book. With reflection to this particular line that he has written in this book, The Argumentative Indian, how do he actually place this geometry of Shulva Sutra and the fantastic mathematics prevalent in Pingala Chanda Sutra? They are certainly much before first millennium CE. Unfortunately, he never responded. Perhaps I am too small a fry to be responded by such a great luminary. But that is the state of affairs. Then comes Chanda Sutra. You see, right on Chanda Sutra itself, I can keep on talking for hours. It's not the time or place for that. I'll just tell you in very crisp manner. As I have started at the beginning, I told you that I'll just stand on certain things in elaborate manner that I did till now. At least 3 of the things I detailed as far as I know about it. Here I'll just refer to certain things, don't have time to get into details of Chanda Sutra. Again, this Chanda is one of the Vedanga and absolutely important discipline and doctrine of the Vedic period. They used to believe that you must master Chanda before you can really read or preach Veda. Without having the mastery in this Chanda Sutra, if you want to read or preach Veda, you are becoming a sinner. That's what this Sanskrit sloka from Brihad Devata telling you. Aviditva rishim chanda daivatam yogamevacha juddhapaye jafid dwapi papiyan jayate tusaha. Without knowing about the rishi and the chanda attached with particular sutras, if you preach Veda, then you are becoming a sinner. Papiyan jayate tusaha. Now, there are a good repository of this Chanda Sutra knowledge, starting with the 2nd century text of Pingala Chanda Sutra. Then you have the Natya Shastra of Bharata, and so many others. The most commonly referred and most important being this Mrit Sanjivani of Halayudha, and the Britta Ratnakara of Kedara. There are so many others. And as I told you, Chanda is one of the most important part of even today's Sanskrit study, the study at the master's level. This Chanda and Pingala Chanda has to be read and mastered. But whatever little bit I have come across to know that they somehow dislike this chapter 8, and they tell that this is so mathematical, we don't understand it. They just skip that particular chapter. This is in the 8, there are 8 chapters of this book, much like Panini. In fact, Pingala is often referred to Paninianuja, not necessarily in the, brother in the sense of, same lineage, rather in the sense of same lineage, maybe some few hundred years apart. Just like Panini has a 8-chapter book, Ashtadhyayi, Pingal also had an 8-chapter book. It's called Pingala Chanda Sutra. And this is these commentaries are absolutely important to understand the cryptic sutras given in Pingala. And these commentaries does help. And one particular commentary, one particular book I'll refer to, because that I will try to draw your attention, especially is this by Virahanka. This one, Britta Jati Shamuchaya. Now this Britta Chanda, and this is not in Sanskrit. All others are in Sanskrit. This is in Prakrit in 7th century. This is something important for my discussion. There are references to Chandas in many other texts like Brahma Sputa Siddhanta or Brahmadutta, but unfortunately that part of text is too corrupted to make any sense out of that. In several Puranas, you have referred to Pingala's work. Pingala himself in his work has referred to prior prosodists, 4 or 5 of them, Roti, Mandabba, and etc., but none of these works are extant. We have no clue as to what they have done. The earliest known is of Pingala, and that itself is an amazing repository of knowledge, particularly the last chapter in the sense of mathematics. Mind you, my friends, Pingala was not writing a mathematical book. He was not writing mathematical texts. He was writing analysis of prosody. But while doing the analysis of prosody, he, with such a flair and flamboyance and such a ease, talked about these mathematical rules that it tells us that the society in which Pingala lived was conversant to this much idea of mathematics. Once you write a book, it is meant for others to know. So if it has to be in the language, it has to be at that level that others should understand it. And that is the reason to believe that this society, 2nd or 3rd century BC of India, the mathematics of that society was so advanced that this beautiful mathematics was readily appreciated by that particular society. So if I just put in a nutshell, I'm afraid I can't get into the details of that. That requires a complete separate lecture on that. I did give such lectures here and there, many places in fact, but that required 3 hours at a stretch, independent on Pingala Chanda Sutra. So I'm not getting into that. I just tell you something, that it can be shown that the basic questions asked in the 8th chapter on Pingala, and there is again one very important subtle point. There are people who claim that this 8th chapter is completely prakipta. Prakipta is that notorious thing that people at a later point of time who has written the thing, they have joined it themselves. It was not in the original text. It is written by someone else at a later point of time. Prakipta. Why? Because if he writes it is by his own name, people will perhaps not pay heed to it. So they write it in the name of existing seers, telling that that seer has told this and that. That is one way of looking at the thing. But if you give time to it, if you read it clearly, you'll understand that the 8th chapter makes sense only when you look at the 1st chapter. The 1st chapter, the way Pingala started his book, the very analysis done in the first 10 sutras makes sense only when you look at the 8th chapter. If you strip the 8th chapter off from Pingala Chanda Sutra, then there is a big question mark that you can place for the first few sutras, that what are the purpose of doing all this. That itself is a proof that the 8th chapter was not a later appendix. It is actually right from the beginning, because the beginning of the book actually paves the path of understanding the 8th chapter, and nowhere else inside the book, in the other chapters, those particular sutras are relevant. So anyway, without getting into much details, which I'm afraid I can't do at this point of time, I just tell you here, just you give me time, I can show you, I'll give you reference. I'll give you concrete reference where you can go through in details to justify this claim and make your own understanding of it, and then stand against or in favor. I have no objection to that. These are interpretations of certain things which I understand and many scholars of history of mathematics understand. But first thing, you must know and then make your own opinion. I am not telling that you have to accept what I am telling. I never preach that kind of things. But I just preach this much, that you know it first. Without knowing, just don't quote others. So in this prosodic book of Pingala, you see binary to decimal and decimal to binary conversion. There's a paper written on that by one Dutch gentleman, Van Newton. It's not by any Indian. This binary numbers in Pingala Chanda Sutra, this was unearthed by one Dutch gentleman. His name is John Van Newton. It was published in a journal called Journal of Indian Philosophy. By the name of the journal, if you think that it is perhaps published from New Delhi, then you are wrong. This journal is published from Holland, from Amsterdam. And there this Van Newton has shown that how this Pingala Chanda Sutras in the 8th chapter can be interpreted in the sense of decimal to binary and binary to decimal conversion. Europe ascribes this to Leibniz, which is about 1800 years after the time of Pingala. There is a Pascal triangle by Blaise Pascal. Everyone of mathematics knows about that. The coefficients, binomial coefficients put in a triangular form. This Pascal triangle in a separate form, not exactly in that pyramidal form of Pascal, but a slanted one, but exactly those numbers with all details found in Pingala Chanda Sutra 8th chapter. Some of the binomial coefficients, credit goes to Newton. What we read our books, you can find it in Pingala Chanda Sutra. And clear reference to mathematical zero as shunya that I have already pointed out. Those 4 sutras of calculating one particular jargon called Shankya. Shankya is not number here. It's one typical jargon, mathematical jargon of one particular combinatorial calculation. And there are 4 sutras referring to it. And 2 of them refer to Shunya, Rupe Shunyam, and Di Shunne. Along with that, there are 2 others, Dir Ardhe and Tabat Ardhe Tad Gunitam. 4 put together leads to a beautiful algorithm. Yes, my friend, algorithm. And even then, this word is explained in Europe as coming from the name of Al-Khwarizmi, who was an Arab about 1000 years after Pingala. He's written the book Al-Jabar wal Mukabala, and it is said that algebra came from them. And the word Al-Khwarizmi gradually Latinized and changed to algorithmy, and then algorithm, which actually initially used to mean doing mathematics like Al-Khwarizmi. But if you look at algorithm, you can find a fantastic algorithm in Pingala itself. That 4 sutras that lead to the formula 2 to the power n, where you have n places, and each place can be filled in 2 different ways, either by a laghu or a guru. These are 2 basic, units of chanda, akshara chanda. There are 2 different kinds of chandas again, akshara chanda and matra chanda. So in akshara chanda, laghu akshara and guru akshara, they are put side by side and they make different kind of meters. And that metrical analysis is done by Pingala. And he asked this mathematical questions that there are some unknown number of places, and the places had to be filled by any of these 2 types. Repetition allowed. Each place can be filled by either laghu or guru. How many different ways it can be done? So how many different ways these chandas can be made? It is a simple question of class 11 standard. For now, whatever you learn in combination, permutation combination chapter. But that algorithm is there, step-by-step algorithm by those 4 sutras, reaching finally to the answer 2 to the power n. This is a book recently written. If you are interested, again, that is also available in, it's a book in Bengali. Unfortunately, if you are not conversant with Bengali, then this will be of no use. But there are other research papers by people at the know. You can try them. This book is I have tried to explain things at great details in lucid Bengali about this 8th chapter. This particular sutras is available in what they call Amazon. Yes. So you can try if you are interested to know more about it. We don't have time to get into the details today. I will just touch upon one particular sutra from Virahanka, that book Britto Jati Shamuchaya, 7th century. He is talking about Matra Chanda. You see, I told you, Varna Britta is Akshara Chanda, and Britta means this is kind of, again, these are all detailed things. Abritta Chanda. So this is repeating itself. These are called Matra Britta Chanda. So when you are measuring the Chandra in terms of Matra rather than in terms of Varna or Akshara, that's a different ballgame. That's what he is telling in the first line. Ebangcha Varna Britte Matra Britta nam annatha bhavati. When you talk about Matra Britta, it is something different. Annatha bhavati. And what is the difference? That is being stated in the next line. Do purbo bikalpo ja miloita jayate shankha. Do purbo bikalpo ya miloita jayate shankha. Now this shankha, as I told you, shankha is referring to that number 2 to the power n. That's a jargon here. And what he is prescribing to get this at one particular stage of n, what you have to do, we have to add the previous 2 stages. Do purbo bikalpo. Purbo bikalpo. 2 of them. That's telling you, in effect, that Sn minus 1 plus Sn minus 2 is giving you Sn. This is the rule of formation of so-called Fibonacci sequence. Do purbo bikalpo ya miloita jayate shankha. And that will give you the number of possible options of a Matra Britta Chanda. This formula will be something different. It is not like 2 to the power n in case of Varna Britta. Matra Britta nam annatha bhavati. And how do you get hold of that? You get hold of that by making this kind of sequence. Just add the 2 numbers, you get the next one. Every time you add the immediate preceding 2 numbers, you get the next one. And that's the number of all possible options of Matra-based forms, the Matra meters. And a reference to this Virahanka is also found in Hemachandra. Even that's before Fibonacci. Fibonacci wrote his book, Liber Abaci, the book of numbers, where he talked about this Indian decimal system with 0. He called 0 as Zephyrum in Latin. That is in 1200 and something, 1202 or something. So this is at least 50 years earlier. Hemachandra, he's writing, Onkanto panto jogaha pare pare matranam. So the same connotation. Onkanto panto, anto and upanto, last and the last but one. Those 2 anka, if you add jogaha, pare pare matranam, the next matra foot, the number of options you can get out of the sum of exactly previous 2. Sn is equals to Sn minus 1 plus Sn minus 2. And still, we people in India are so very happy to call it a Fibonacci sequence, and not a Hemchandra sequence, not a Virahanka sequence. Well, people like Manjul Bhargav in his lecture is now advocating that one should talk about this as a Hemchandra sequence, or at least Hemchandra Fibonacci sequence. You see, most of us, mathematics students, if you are on the other side, you know a very famous inequality, Cauchy-Schwarz inequality. That's the most common thing in mathematics. That was the most celebrated inequality of whole mathematics. My friends, you go to Russia or get hold of a Russian textbook, they refer to it as Cauchy-Schwarz-Bunyakovsky inequality. In the Russian books, you will find this name, Bunyakovsky. Because Bunyakovsky is a Russian mathematician who has done it. Russians believe that independent of these 2 people. So in their books, they write Cauchy-Schwarz-Bunyakovsky inequality. But even in our book, we don't write Hemachandra Fibonacci sequence, talk about Fibonacci sequence. Because we have been told to learn things and write things accordingly. Then it comes to Bakshali manuscript. Bakshali, that's the Birch bark manuscript that was unearthed in a place called Bakshali, which is some 80 kilometers apart from modern day Peshawar. It was unearthed by one peasant. Suspected. He was just excavating his land, preparing it for cultivation, and suddenly got hold of this manuscript, which is almost damaged to the extent of irrecoverable situation. And then certain things happened. I don't have time to get into details. Once again, if you are interested, I'll give you references. I've written articles on Bakshali manuscript in Bengali. I'll give you the references. If you're interested, read that story. But what is interesting in Bakshali manuscript is amazing level of mathematics in it, and replete with number 0, written numeral 0 in the form of dot, those bold dots. Remember that Subandhu reference that I told you, that Vasavadatta, Shunno Vindavaha. So you'll find this Shunno Vindu, the written dot 0 numeral. And all these are written in decimal system in Bakshali manuscript. So it is very difficult to swallow for Eurocentric scholars if Bakshali manuscript gets dated in 3rd century BC. I'm sorry, 3rd century AD or 4th century AD. This is the time when Takshila was being plundered for good by the Huns. That's the final damage. Who knows that some people from Takshila, some seer from them has got this knowledge somewhere, tried to write it down. There is a colophon in this Bakshali manuscript talking about a person called Chajaka. He's a son of somebody else, and he is telling that I am writing this for the usage of the son of something, some other people by the name of this and this. He's referring to himself as a prince of calculator. His name is Chajaka. He's son of Hashika, and he is writing it for one particular family. There's a kind of mathematics book. So many problems are solved here. So many mathematical problems with complete solutions. It's written in the Gotha dialect of Sharda script. Now, this was prevalent in Kashmir region at that point of time. And recent carbon dating, as you can see, this was so, badly attacked, this Bodleian finding, immediately by the Eurocentric scholars, and they are so big name that Bodleians actually stepped back and they never actually published their findings in a peer-reviewed journal. But I do have a copy of that. I did contact Bodleian people, and they were nice of them that they have shared a copy of the finding of the whole thing. They have the whole statistical analysis done of the carbon dating, and it shows that 95.4% probability of correctness, that formal language is called confidence interval, as the statistical analysis are done. So all things are there. Their methodology, what they have adopted, and these are the timelines that they have actually found of these 3 particular folios, 16, 17, and 33, that they have put to the carbon dating. There are 70 such folios kept in such a kind of book. You can have an access to it. You can touch it. It is amazing only to know that this actually was deciphered right here in Calcutta. After this was found in Peshawar, is the British period in 1881. This is the time we are talking about. Calcutta was the British capital at that point of time, British capital of India. So it came ultimately to Calcutta Madrasa. The director was Professor Hornell, and he was an extremely competent person of deciphering these old texts. And he actually deciphered Bakshali manuscript for the first time, and has written several papers and presented them first in Asiatic Society and then in Germany and other places. And then in his lifetime, when he thought that he cannot take hold of this great responsibility of this priceless document, he has sent it to Oxford, and from that point of time in 1910 or something, this is kept at the Bodleian Library of Oxford. It's an Indian document, but no Indian is permitted to even have a closer look to it. We are interested, we talk about the Kohinoor, that why should the Queen wear the Indian Kohinoor, and they should give it back to us. And to me, an humble student of mathematics, this is even more priceless than Kohinoor. Nobody ever talks about bringing back Bakshali manuscript to India. So they have taken everything of us, including such priceless documents of our civilization. Anyway, this has been, pictured by modern technology, and with respect to that pictures and etc., this has been deciphered, read, interpreted right from the time of B.V. Datta. And here you see this is one particular page by Bill Castleman, and you see these numbers there. These are Bakshali scripts of number 7250. This is 0 over here, right? And this number, please remember it. I'll just come to it in few minutes, that what is the significance of such a large number. This is actually one way of writing fraction, right? Bakshali manuscript, they used to write fractions by this. There was no separator line. There was no separator line between these two, right? This is the numerator and this is the denominator. Now this fraction is referring to something absolutely amazing. I'll come to that. I'll shortly come to that. But remember, this is 5, 0. Can you match that? 7 here. This is 7. Can you see that? This is 7 here and 7 there as well. So this is the number. This is how you can read Bakshali manuscript once you know that how it is to be read. And this is the magazine Bigyan Kotha, published by Bigyan Prashar. It's an autonomous body under Department of Science and Technology, Government of India, which is publishing Bengali journal Bigyan Kotha from last year. So this is in 4 successive issues, October, November, December, and January, that I have written about Bakshali manuscript. So those who are interested can go. This is free, available in net. You just go to the site of Bigyan Prashar, write Bigyan Kotha in Google, and you will find all this. So in the October, November, December, January issue, you can just download and read a little bit of what I have written over there. But today I'll just talk about one particular issue on Bakshali manuscript that will, I'm sure, mesmerize you. That will simply mesmerize you with the understanding of mathematics that these people had at that early era. This is the page I was referring to, right? That particular page. And this is the Bakshali scripts of numerals. 1, 2, 3, 4, up to this is the 0, right? And this is the page 46. This is the number. And this number has been recovered by scholars after detailed calculation. Some of them has gone for good. As you can see, these are all torn, mutilated, but the rest is matching. So accordingly, calculating right from the beginning, the other thing has been actually this is here, the color red, that these were there actually in the whole bark had then been available to us. But these are what we have, and this is what is lost. The red part is lost, but this has been actually reconstructed by historians and mathematicians who calculated on this. There's one great scholar working on it, Takayo Hayashi, Japanese, on Bakshali manuscript in present days, along with many other scholars like Kim Plofker, Clemency Montel, and many others. Anyway, so, but with a Eurocentric bias, some of them, of course, because they are not ready to accept Bakshali manuscript before 9th or 10th century. Because 9th century India is writing 0, that cannot be refuted. That 0 is to be found in the Gwalior fort. It's, engraved in stone. No one can refute that India was writing natural, normal 0, not this bold dot 0. The further evolution, 0 became the way it looks now. And that 0 is engraved in the walls of a temple, Chaturvuja temple in Gwalior fort. So they are Eurocentric scholars. They are keen to bring down Bakshali after that. It's 9th or 10th century. Then it actually fits their doctrine that India started writing much later, and these all came to India from Greece, and then from Varahamihir time onward they started working with it. Then came Aryabhata, but everything these people did as actually they learned it from Greek people, and then worked on that and did something new, etc., etc. But origin is actually Greece. That's that doctrine, right? So accordingly, they are very, very skeptic. They are very, very, it's not up to their taste to accept Bakshali. It was very difficult for them, and they have written very caustic remarks regarding this Bodleian finding of C14. Now, C14 carbon dating is a standard practice of finding the exact date of ancient objects, artifacts of which carbon dating can be done. This is something physics, chemistry people can explain much better what this C14 dating is. This is, you can also Google and come to know that how this radioactive carbon element, its half-life and all these things, that you can back calculate and find out the time of the origin of this bark, because it comes out of this bark of the birch tree. It is responsive to carbon dating, and that's how it was done, and done by Bakshali people, done by Bodleian people, Oxford University, not here in India, not by any political party, but then still there are many people who are reluctant to accept this. But anyway, these are all academic discourse and historical things. They do proceed in this way. You see, this is not science that everybody has to accept that 2 + 2 in decimal system has to be equal to 4. There is no less than 4 or more than 4 till you are ready to stick to decimal system. Proofs of history come in a different way, in a roundabout manner. There are always ways of interpretation and all such things, academic discussions and discourse. Well, that is most welcome. There's nothing wrong in it. But then it should, again and again, what I would like to tell is this, that people should at least know what is what, and then form his or her own opinion to take a side. You see, I just take you to one single before I finish. I think it's already almost 2 hours that I have been talking. I just take one more single example from Bakshali manuscript to leave you mesmerized after the lecture. This is approximate square root rule. It says, Akrite slishto prityuna sheshochedo dishanguna tad barga dala shanslishta iti shuddhi kritikaya. Now, Bakshali, if you go through the manuscript itself, you will see that such sutras are mentioned, and then there are some word problems, and at least 5-6 word problems explaining the sutras, the implementation of the sutras, solving problems using the sutras. Luckily, yes, luckily, because out of this procedure of solving, we could reconstruct the meaning of these sutras. Because Bakshali people, as has always been in India, never bothered to tell us how did they get hold of this sutra. What is the proof of this sutra? The proof, so-called, the way we understand proof today in mathematics and appreciate proof today in mathematics is essentially Greek in nature, the deductive argument. Indian knowledge system, there was no such idea of deductive argument of proof. There's a completely different genre. That doesn't mean that there was no proof in India. They didn't know it. If they didn't know, then how could they use these results so successfully in all of them? This is not like, empirical knowledge, like once you can see in Babylon. There is a clay tablet called Plimpton, where you see that numbers of triplets are written, a series of triplets, and you are amazed to find that those numbers are actually Pythagorean triplets, about 1,000 years before Pythagoras. But only the numbers are written over there. So maybe that they came across the number while doing some construction work or etc. Such thing was known to ancient Egypt as well. People who constructed those tremendous engineering constructions, this Pythagorean property of numbers in a right angle triangle automatically came to them. But proof, whatever we call proof today, that deductive pattern of argument, you can find only in Greece. And since we accept that as a modern way of looking at mathematics, that is what we learn in our schools and colleges. That's how you prove things. But that doesn't mean that every ancient knowledge system had to have that kind of proof. There was a different kind of thing in India. You have to appreciate that as it was, not through the prism of Greek mathematics. That's a very important thing to appreciate and understand. And there was a different way of accepting and verifying the way Indians used to understand that. Anyway, what is unfortunate is this much, that the clue is not there, that how did they get hold of these results, so beautifully efficient, so apt and accurate. But luckily, since they have used it in at least 6 different sums, that is found in Bakshali manuscript, we are quite sure about the meaning of this sutra. So I just explain it here. Please be with me for 5 more minutes and see how astounding this sutra was. So Q is a number which is not a perfect square. It's in our language. And I'll apply the sutra, translating it in our language so that we can really easily connect. It says Okrite. So Krita is perfect square. Okrita means which is not a square. So you have to do something on it, which is a jargon, slishta. Slishta krityuna. So what is being done here as per the exercises or the examples done in Bakshali? They take out the nearest perfect square part out of it. So you write Q is equal to A square plus R, where A is the nearest perfect square inside Q. R is the extra part. So that's the slishtokaran, the slishtokrityuna, sheshotchedo dishanguna. So out of A square, what is the first approximation? Had it been just A square, the number would have been A, the square root. But it is not A square, it's more than that. So it has to have a tail. And what is that tail? Sheshotchedo dishanguna. Shesh is the remainder, the residue, the extra, the additional part, R. That A square plus R. That R is the shesh. Cheda is division. Dishanguna. So it has to be divided by twice that approximate value. The first approximation is A. The second approximation that I have written here as first approximation, actually first approximation should be A itself. The second part of it, when A is refined further, is to add A R by 2A. Sheshotchedo dishanguna. Then the next. Tod burger. So this A plus R by 2A is to be squared. R by 2A, that shuddhi, that correction part, that has to be squared. Burger. R by 2A whole square. Dala sangslishta. Dala means divided by 2. So R by 2A whole square is to be divided by twice as much of the first approximation. That's sangslishta karan. So these are jargons used here. Slishta and sangslishta. Right? And that amount is the shuddhi, the correction. A plus R by 2A was the first. A was the first approximation. R by 2A, the first correction to it. And then this is the shuddhi, kritik khaya. Khaya means subtraction. It has to be subtracted. And why kriti? Kriti is the square. I'll show you that this formula is reached by actually ignoring a perfect square part. Kritik khaya. You have to ignore that square of the error because that will be even smaller. And that's why you are interested in the approximate value only. So that square of the error has to be neglected and you get this formula. A plus R by 2A minus R by 2A whole square plus. And then it's just apply it here. This is a simple application we have done here. Root over 10. So 10 is 3 square plus 1, as simple as that. Then according to the formula, it is 3, that is A, plus 1 by, it's a R is 1 here, by 2A. So 1 by 6 minus the square of that, 1 by 36 by 2 into 3 plus 1 by 3 plus 1 by 6. Now help yourself with the calculator and find that this is the value, which is the direct value. If you can directly calculate root 10 by your calculator, you will see that this matches 5 decimal places. Now, why this is so tremendous? Yes, it itself is fantastic. But why I am so, charged, that is to say, with this particular one, I'll show you why. First of all, this is the algebraic description of the formula done in today's language. Q was A square plus R. So where from this suddenly this A plus R by 2A comes? It comes through this avenue. You just rearrange A square plus R in this manner. You take A common, then write this as 2R by 2A, and then you write it this way. Sum and difference. R by 2A plus R by 2A, and this is R by 2A minus R by 2A. That is this first A, right? So this is A plus B into A minus B, and it looks like this. And you accept the first one, neglecting this. Can you see that? Kritik khaya. You neglect this. And what you get is this. This is a perfect square term. And the square root of that is, of course, your approximation. It's not the exact value, so it is A plus R by 2A. That's the first part. And then, if you want to get one step further, of course, square root of Q is not A plus R by 2A. There is an error in it, so you just add one E to it. That's the error part. And then simplify and try to assess the error. So this is squaring both the side and simplifying 2-3 steps. Very usual, very usual calculation of algebra. You reach this step. where you have this equation here. E square, E is your error, mind you. This is E square plus twice E into this equal to this. So you neglect this A square, E square. That's a square term or error neglected. Kritik khaya. And then E has this formula. R by 2A whole square by twice A plus R by 2A. So that's your E. So the better formula, better approximation, the second phase of approximation is this. Square root of Q is this. This is your E, but only neglecting E squared. Iti shuddhi kritik khaya, right? And these are application of that in one particular problem of finding a rational approximation to the solution of this equation. They have come across this number 336009. The square root of that has to be calculated. And there they have applied this formula. 336009 is 579 whole square plus this. And then you are applying this formula. Believe me, I don't have time to get into the details of that calculation. It's not difficult. Step by step, the same formula is being done. And once you reach this formula, finally, what you get is this value. This value you can check, it is correct up to 13 digits. What they used to do is something fantastic after that. They used to put that in the original expression and check it, whether the calculation was correct. And that checking gave rise to this number, that exact equal to 7,000, that you have to put that back, this approximate formula, balancing its approximation. You have to put it in the original formula and simplify. And after that whole page, that page I have shown you, you remember this number 7250 and ending with so many zeros? This is that particular calculation. That number divided by this number is exactly 7,000. And that is this page, the page I have shown you earlier. Remember that? Here, this number, 507. Remember? And this was the denominator, 7250, ending with so many zeros. That's this calculation. The prior steps of calculations are shown here, here. So they were talking about these large fractions, not in decimal points. They are fractions. They are representing them in fractions, but doing such tremendous amount of arithmetical calculation, and that is in decimal system and using zero as a number in its own right, calculating with zero at that early period of time. Finally, why is it so important? Now I talk about Newton-Raphson method. If you are a student of mathematics, you are already aware what this is all about. So this is some, 17th century mathematics. And we are there in 4th century in Bakshali. And here I see that Newton-Raphson is telling that if you have a function fx equal to 0, you want to guess a root of it. X0 is an initial choice. Then x1 is a better choice if you do this by calculus. This is what we teach in classes, right? Newton-Raphson method. This is a part of the syllabus of undergraduate text. Numerical analysis, right? X1 is equal to x0 minus fx0 by f dash x0. And that's a better approximation. And you have a general formula with, of course, the assumption or the restriction that f dash xn should not be equal to 0. Do this on Bakshali. Do this on the Bakshali calculation, x square equal to s square plus r. That's what we started with in case of Bakshali. So take the function fx equal to x square minus s square minus r. Apply Newton-Raphson. The first is A. That's the first stage of approximation, x equal to A. And that's your x0. So what will be x1? x0 minus fx0 by f dash x0. So just simple derivative. To do that, x0 minus fx0, that's minus r. And this is twice A, the derivative of that at the point x0, which is A. So that's what you get, A plus r by 2A. Then go for the second stage, x2 equal to x1 minus fx1 by f dash x1. It's not difficult to just simplify, calculate, and bingo. There you have the Bakshali formula. Without calculus, the Newton-Raphson formula, some more than 1,000 years before Newton's time. This was the level of mathematics India attained at a certain point of time. I just keep on talking about many more things, but I don't think I have time for that, nor is it necessary. I rather leave with this famous quotation from A.L. Basham, the wonder that was India. He says that most of the great discoveries and inventions of which Europe is so proud would have been impossible without a developed system of mathematics. And this in turn would have been impossible if Europe had been shackled by the unwieldy system of Roman numerals. There was no zero in
Yes.
Roman
Yeah.
system. There's not a place value system. It's a very clumsy, absolutely clumsy system. When you write 5 and write 1 to the right of it, it becomes 6. But write 1 to the left of it, it becomes 4. But when you write 100, C, and write 1 to the left of it, it doesn't become 99. Absolutely clumsy thing to do. The unknown man who divides the new system. This is the decimal system with 0 he is referring to. This unknown man who devised the new system was, from the world's point of view, after the Buddha, the most important son of India. His achievements, though easily taken for granted, was the work of an analytic mind of first order. So this is the Gwalior fort I was talking about, where you can go and see the 0 engraved there. The oldest known, written, modern 0, which is accepted by both the parties. There are many other engraved 0s, but those are on copper plates, and their authentications are, experts are not of same opinion about them. Some says that they are fabricated, some says they are original. But this one, if you go back, this one is undisputed. But this is only very late in 9th century. And that is this 0, the oldest known 0 in the human civilization. The modern 0 in the oldest known 270, that is written here in the Chaturbuj temple. This is one king, Mihir Bhoja. There's an inscription made by that king. There's a land grant charter, which is inscribed on stone. This Chaturbuja, that is Vishnu, a particular area of land was being granted for making a flower bed, and this is the length of that land, 270. Luckily, the number used some zeros, so we know this. So we get hold of 0. It was 270 hasta in length and 187 hasta in breadth. We are so fortunate that it was 270. So a 0 was needed to write that we can claim that at least at that point of time, come you people and you see that India used to write 0. Had it been something else, perhaps Eurocentric people would have claimed that it is even much later that India started writing 0. Now, these are something very hilarious, but then this is the sorry state of affair as it stands now. So this one is historically the oldest known inscription of the modern 0. If you go back 200 years more, then you get this inscription of .0 in stone. That's in old Khmer language. This is in Cambodia. At that point of time, under the Buddhist cultural dominance, this is written about 605. The Shaka era has reached 605 on the 5th day of the waning moon. That is written in this line. And this 605 in the old Khmer, this 0 is, as you can see, this is the bold .0, that Bakshali 0. This is some 683, if you calculate after using the Shaka correction, 7th century. Bakshali is even at least 300 years older than that. So I think with that, I should end here. Thank you very much for your patient hearing. I'm afraid, and I apologize that I could not do much justice to this tremendous subject with a monumental volume of articles and research materials. But I'm convinced that if you find it interesting, then you can go by yourself, dig it deeper, delve it deeper, and read it yourself. You are all educated people, so I invite you to frame your own opinion rather than like a parrot just mimicking others. Thank you very much.